guys, welcome to another video in the series of coding. Today we're going to do the problem which is called longest nice subarray. So this is a very beautiful question. Personally I like this question very much. Let's get started to it. So you are given some array. You have to first of all find a continuous subarray in this array which is of maximum length such that if you take the AND of every pair of elements you will get 0. Okay, let's try to take an example to understand. They have given us that 3, 8 and 48 are satisfying this condition. Let's see. If you do 3 and 8, you will get 0. Okay, what is the meaning of AND? First of all, you have to write the number in the binary representation. What is 3? See, binary representation is just 2 power 0, 2 power 1, 2 power 2 and all. If you just fill what will be the value. So what is 3? 3 is just 2 power 1 plus 2 power 0, right? So 3 is just 2 plus 1. So here you just write 1, 1. This is equal to 3. So this is 3. Now similarly, let's write 8. What is 8? 8 is simply 2 power 3, right? So 8 is 2 power 3. 2 power 3 will come here. This is 2 power 2, 2 power 1, 2 power 0 and so on. So in simple terms, this is the binary representation for 3 and this is the binary representation for 8. If you take the AND of these two numbers, what are you going to get? See, the AND means whenever you have 0 and 1, the AND of that will be 0. If you have 0 and 0, the AND of that will be 0. If you have 1 and 1, the AND of that will be 1. So AND is just basically multiplication in simple terms. So here you see, at all the positions, if you take the AND, you will just get totally 0. Because there are no positions where the set bits are matching. Set bits means just where 1 is set, right? So for 3, you can see that 1 is set at these two positions. Okay, but in 8 the 1 is set here. So there are no places at all where the 1 is matching. When will you get an AND 1? Only when 1 and 1 match, then only you will get an AND of 1, right? In all other cases you will get 0. If here I had a 1, then here I would have got 1 and 1 equal to 1. But here I don't have a 1, right? Both have set bits in totally different positions, right? In totally different spectrum. So because of which their AND is totally 0. Okay, for 3 and 8 we saw. Now let's see for 8 and 48 and let's also see for 3 and 48. So for all the pairs in this subarray, AND is equal to 0. Okay, let me write the binary representation for 48 now. So what is 48? If you write 48, see 2 power 5 is equal to 32. So first you will have 32. Then from 32 you have 16 left. So that will be 2 power 4. So 2 power 5 plus 2 power 4. So this will be 2 power 5, this will be 2 power 4 and then you have 2 power 3, 2 power 2, 2 power 1, 2 power 0. All this is 0. So for 48 if you are seeing, the 1 is in even further positions, right? So here if I continue, for 3 and 8 I can write here zeros. So this is the totally binary representation for 3, this is the binary representation for 8, this is the binary representation for 48. Again you can see that the ones are all in actually different positions. So because of which you are able to see that AND between all the elements is equal to 0. Now this question is very interesting. See, if you calculate for all the pairs of element, the time complexity will be order of n square, right? You cannot do this. For each and every pair, you can just not calculate. And that also you have to take it within a subarray, right? You cannot first of all calculate all subarrays and then inside subarray calculate for each pair of elements. So then if you take the worst case, it will be even larger than this order of n square. So you did not even think of all those approaches. First of all, it is given us a continuous subarray, right? So whenever it is given a continuous subarray, the first thing that must come to your mind is a sliding window technique. In most of the cases, sliding window is the answer, because the subarray is equal to continuous. So whenever a subarray is continuous, what is the sliding window technique is, you try to take elements till which you are able to satisfy the answer, right? For example, I am taking 1 and 3. I don't know if like these two have an AND of 0 or not. I am just telling. Let's say 1 and 3 satisfy the condition. I am just explaining the sliding window technique, okay? Let's say 8 also satisfies the condition, okay? Let's say you see element 48, which if you include in the sliding window, it will not satisfy the condition. So then what you do is you remove elements from the backside and you try to see whether these 3 will satisfy the condition. Let's say these don't satisfy the condition, then you will remove element from the backside. Okay, let's say now it satisfies your condition. So then you will add element further from here and you will continue with this subarray and so on. So this is the sliding window technique. You add elements from one side let's say you have a front pointer I from which you keep on adding elements, and you have a back pointer j from which you keep on removing elements. So just in order of n complexity you can solve such questions which have continuous subarray type problems. Okay, so let us see in this case how we are going to solve, and it will be clearer. So what is 1? Okay, let's start with the binary representation of 1. Okay, let's take a number where we are going to store wherever we see the bits as set. Okay, let's see a dry run, then it will be clearer. 1, what is 1? Okay, first let me write a very big number. Okay, this is this is a very big number. This 2 power 0, this 2 power 1, this 2 power 2, 2 power 3, 2 power 4, 2 power 5. Hopefully this will cover up to 2 power 32. This number obviously, let's consider the bits as 32, then it will go up to 2 power 32, but we need not consider that. Within this we can see the dry run for this. Okay, let's start with the number 1. Now when we see 1, what is 1? 1 is equal to 2 power 0. So this bit is set and all other bits are 0 in this number. Okay, so we can include the number 1. Till now 1 has no problem with anyone. 1 is the single element, 1 is the king. 1 is going to come here and say that this bit is set. Okay, now let's try to include 3. What is the binary representation of 3? Now let's see, if we include 3, do we have any problem here? What is the binary representation of 3? For 3, if you see the bits which are set, 3 is 2 power 1 plus 2 power 0, right? So for 3 you will have these 2 bits as set, right? These 2 bits will be set. But if these 2 bits are set at the same positions, the AND of this will not be 0. Okay, it will not be 0 because the AND of this will come 1. Okay, here you will get a 1. So these two have a problem. They don't like each other because their AND is not becoming 0. So if you include 3, you cannot include 1. Okay, so what we do, we are going to remove 1, because see, if we cannot have a subarray which is discontinuous, right? Since it has to be a continuous subarray, right? If you have to go forward, you cannot have a subarray in future including 1 also. You cannot take this subarray because this 3 has a problem with 1, right? It doesn't matter what future elements you are taking. If 3 has a problem with 1, you can never include 1. So if it is a continuous subarray, you have to remove 1, then only you can go ahead with the next future elements. So always we remove from the back side. Okay, so now unfortunately we have to remove this element 1. Okay, so we will remove this element 1. 1 already put its bit set, right? 1 already had set its bit in number. So how do you remove it? Just do XOR. Okay, so just do XOR of 1 with this number. Okay, why? Because see, what is 1? 1 is this number, right? 1 was this number. Okay, 1 is this number. Now if you do XOR, what XOR does, whenever you have same positions, it will unset those bits, right? So 1 and 1 is equal to 0 in what? In XOR. XOR means whenever you have same 1 and 1, 1 XOR 1, 1 XOR 1 is equal to 0, right? So if you just do XOR, you are going to unset this bit. So that is what we want. We want to remove 1. We don't want the bits of 1 because 1 has a problem with 3. We cannot include them together. So unfortunately, we will have to do the XOR. Okay, we will do the XOR of this number with 1, and because of which this number has again become like this. Okay, so by the way, how are we doing this? As I said in the beginning, we have 2 pointers. One pointer is here and one pointer is here. So this number is gone. So now our j pointer will also move here. Okay, so this number is gone, so I and j both are pointing towards 1. Okay, now 3 can be included. 3 no more has a problem with anybody. 3 had a problem with 1, that's why we couldn't include 1, but now 3 has no problem sitting alone. So what we can set the bits of 3. So what are the bits of 3? 3 is 2 power 1 plus 2 power 0. So here we can set the bits of 3. Okay, now we will move forward. When we move forward, what we are doing, we are simply moving the I pointer forward. Okay, j will remain there, I will move forward. So now 8. What are the bits of 8? Let us write the bits of 8. Okay, bits of 8. 8 is simply 2 power 3, right? This is equal to the binary representation of 8. Now 8 has no problem with num. We can just do AND of these two numbers and check. Now if you do the AND of these two numbers, it will be 0. Okay, it is 0 because see, here only the bit is set, and 1 and 0, here it will give 0, and all the places also it will give 0. Okay, no problem at all. So we can include 8. So if we include 8, we can set the bit here. That means we are including 8. Okay, include 8, and we can move forward. Now let's go forward. No problem till now, no problem at all. Now let us go to I equal to 3. Now we see the number 48. Now let us write the representation of 48. What is 48? Okay, 48 is 2 power 5 plus 2 power 4, right? 32 plus 16. So the binary representation of 48 is this. Consider this number and consider this number. If we include 48, do we have any problem? We don't have any problem. Now what is the advantage of this is, see, we took a number, right? In this we have included the set bits of 8 and we have included the set bits of 3. So this number contains the set bits of both 3 and 8. So we need not separately check with 3 and 8. We need not check again and again. This is where we are saving time. This is very important. In just by checking the AND of this number and 48, we can check whether 48 has a problem with either 8 or 3. Because this number includes the set bits of both 8 and 3. That's why in this number, the set bits of 8 and 3 both are included. Okay, so now just by checking with this number we can find out if 48 has a problem with either 8 or 3 or not. So 48 has no problem. You can see that the set bits are all very different. If you take the AND of this number entirely, the AND will be 0. So it is awesome. So now we can include the set bits of 48 also in our number. So we will include the set bits of 48 in our number and we will continue. Okay, so now this is the number which includes the set bits of, this number includes the set bits of 3, set bits of 8, set bits of 48. Okay, these are the set bits of 48, these are the set bits of 8, these are the set bits of 3. This number includes the set bits of everything. This is a very awesome number. Okay, so now let's continue forward. Now we go to I equal to 4. When we go to I equal to 4, we see the number 10. Now let's write the binary representation of 10. 10 is 8 plus 2, right? So 2 power 3 plus 2 power 1. So the binary representation of 10 is going to be something like this. Okay, now this is a problem because if you take the AND of these two numbers, what is going to happen here? It is not going to give you a 0 number, right? Because see, here the bits are matching. So this, the AND of this will be something like this, which is a non-zero number. So 10 has a problem. Okay, it has a problem with somebody. Okay, we don't care with whom it has a problem among these, but it has a problem. Okay, because in this number somewhere the bit is already set and 10 is also doing that. So what we have to do is, we cannot include 10. If we include 10, this is not a valid answer. So we have to remove elements. But we cannot remove elements just like that. We have to take continuous elements, right? In the question it's given, you have to take continuous elements. So you have to remove elements on the back side so that this remains a continuous subarray. Okay. So now we will remove the bits of 3. How are you going to remove the bits of 3? Okay. Now let's remove the bits of 3 first of all. So let us write the binary representation of 3. What is 3? 3 is 2 power 1 plus 2 power 0. Okay, this is 3. Now, these were the bits which were set in 3. Just remove it. How can you remove? Just take the XOR of these two numbers. If you take the XOR of these two numbers, wherever the bits are set, wherever the bits were same, right, those bits will become 0. So, here if you take the XOR of these two numbers, what will happen is these bits will fly off. So we have removed the bits of 3. You can see that when we make these values as 0, we will remove the bits of 3. Now 3 is no more included in our answer. Okay. Now what we can do, we can again check if 10 still has a problem with this number. Okay. Let's again check. So now we have to write the binary representation of 10. Okay. Before we write that, by the way, if when we have removed 3, we will move the J pointer forward. Okay. Now let us check the binary representation of 10 again to see if it still has a problem with the number. What is 10? 10 is 2 power 3 plus 2 power 1. Okay. So this is 10. Now you can check again the AND of these two numbers is not equal to 0. Here somewhere we are getting a 1, right? The AND of these numbers is something like this. So this is a non-zero number. So 10 still has a problem. 10 still has a problem with any of the numbers. We don't know with which number it has a problem, but with any of these numbers it has a problem. So now we have to remove 8 also and try to check if 10 is okay with. Okay, now let's write the binary representation of 8. 8 is this. So what we will do, how to unset the bit of 8? Just do XOR. If we do XOR of these two numbers, what will happen? We will unset the bit given by 8. So when we do the XOR of these two numbers, the bit which was set by 8, this bit, right, this bit, we can remove it. So this bit we can go and unset it, and when we do this, what will happen is we are moving our J pointer. Actually we'll move our J pointer to here. Now let us again check if 10 still has a problem. What is the binary representation of 10? So 10 is equal to 8 plus 2 which is 10. Now you can see that if you take the AND of these two numbers, 10 has no problem because the AND of these two numbers is equal to 0, right? So 10 should not have any problem now because the AND is equal to 0. So you can include these numbers. Now we can go forward. Now next time when you go forward, I will be equal to 5. Okay. Now what we did when we this is the total process. When we did, okay, we need to keep a store of answer, which was the maximum length that we got. You could have seen that in between there was a case when we got 3 elements. How can we keep track of the length of the subarray? Length of the subarray is very simple, I minus j plus 1. Okay, let's take one example. So what were our elements? 1, 3, 8, 48 and 10. So in between when we saw the example, there was one case when j was equal to 1 and I was equal to 3. This case was a valid case, right? So this is where you would have got the maximum length. We can keep a store of this variable and find the answer. So I pointer was pointing at 3, j pointer was pointing as 1, and the value of this will be equal to 3. So the length of the maximum length which gives this condition is 3. You can return 3 as the answer. Okay, this is the output. Now let's go forward to coding it. Very beautiful question, sliding window technique, and also bitwise operations we are using. So first of all, we are going to iterate over the entire array. Okay, now what we are doing, we are keeping one number. This was the number that we are always keeping, right? This num we took, which was a representation of, which included the set bits. Num had the set bits, right? Num had the set bits of all numbers in the subarray, right? Of all numbers in the subarray. Num is that number which has the set bits of all numbers. So we will keep a number. Initially we can make it 0. Okay. Now what we can do is we can have a pointer j which is going to be behind I. Now we can just check, okay, if the AND of this num and the current value, which is nums of I, right? So we can just check if the AND of these two numbers, if this is equal to 0, then it is awesome, right? Till now there is no problem. If the AND of these two numbers is equal to 0, it is awesome. But if this value is not equal to 0, then only you will have a problem. Okay, so if this value is not equal to 0, so we can give the condition while this value is not equal to 0, right? There is a problem. So problem because the current element has a problem. With which number it has a problem, we don't know, but we have to keep removing numbers from the back side unless this problem is solved. Because in our subarray we need to have the AND of all pairs as 0, right? The AND of all pairs should be 0. So if it is not equal to 0, there is a problem and we need to keep removing numbers from the back side. So what we are going to do, how can you remove numbers from the back side? So very simple, just do XOR as discussed, right? Nums of j, XOR with this number. So num, our number, you can just do the XOR with this. So this will unset the bits, okay, set by nums of j, because whenever you do XOR, whenever the bits are same, right, 1 and 1, 1 XOR 1 will become equal to 0. So whatever bits were set, that will become unset, right? So this is a simple condition. And now you can also increase your j. Okay, so this will keep happening. Now after this loop is done, now your element will no longer have a problem with any of the elements. The AND will become equal to 0, then only this while loop will exit. So if the AND is equal to 0, that means you have no problem at all, right? So here you have no problem. The AND is equal to 0. So if you have no problem, then it is awesome. What you can do is you can set the bits of num with our number. So this is where we are setting bits inside num, okay, with our current element. So wherever our current element has a bit equal to 1, we will also set it in the number, right? So that is this is what we are doing. So that's it. This is a simple problem. Now we can also keep a variable answer. Let me declare a variable answer. Answer is equal to 0 and answer will be equal to maximum of answer, comma, the maximum length that we get. So to calculate the length, the formula is I minus j plus 1. Now we can return answer. So the time complexity of this is order of n, and let's run and see. It should work. It's accepted. Thank you for being patient and listening.